Okay, let's have a look at another type of locus problem that comes up. It's this sort of problem where they tell us omega, or some pronumeral, is equal to some function of a complex number. And then they want us to find either the locus of omega or the locus of z, where they'll give us some condition for the other one, so omega or z. The idea is make whatever they're saying. They've given you a condition for omega, then you want to make omega the subject. If they've given you a condition for z, you want to make z the subject, because that's the thing you know. So you need that to be the subject. A couple of things to look out for. If they mention omega is purely real, now you can solve this algebraically by saying, oh, well, that means the imaginary part of omega is equal to 0. And then break up the omega into the real and imaginary parts, and you can come up with a Cartesian equation. That, of course, works. But you can think of it visually as well, in that we now know that if it's real, that means its arguments will be either 0 or pi. 0 or pi. And so we'll see in the typical sort of question we look at, it ends up being the locus will turn out to be a straight line in some of the ones we'll look at, but more on that later. Imaginary, again, algebraically you could do it by saying the real part is equal to 0, but visually we'd be saying, well, the argument's either plus or minus pi on 2. So same sort of idea. Now, yesterday we saw that the argument of some z minus something is array. When it's actually this, notice it's not just a linear function in there. When it's a linear function divided by a linear function, this will turn out to be an arc of a circle. And we'll do an example of that in a sec to demonstrate why that happens. Now, it turns out if that angle that they're talking about is bigger than pi on 2, then it'll be a minor arc of the circle. And if it's less than pi on 2, it'll turn out to be the major arc of the circle. And if it's equal to pi on 2, it's the semicircle. So let's have a look at a few examples. So here we go. We've got this function. W is equal to z plus 2 divided by 2. The condition they've given us is on z. We know that the modulus of z is equal to 4. So first thing I want to do is make z the subject. So if I rearrange it, moving some terms around, there we go. So z is equal to 2 on w minus 1. But I know the modulus of that is equal to 4. So I can now say, well, that means the modulus of 2 on w minus 1 is equal to 4. I can now go and find the locus of w. Well, let's play around with this a little bit, because the modulus, or the absolute value of 2, is 2. I can turn it upside down, divide by the 2, and I get something I recognise. I've got the modulus of w minus 1 is equal to a half, so therefore the locus is circle.
In the question itself.
So we know the locus, centre 1, 0, radius a half, and I've given it its Cartesian equation as well to describe it fully. Now, actually, I'm glad you brought up that point that should have been on z, because we always have to go back to the original question and see, well, does every point on this circle satisfy the original? The only problem we're going to have in the original one here is, of course, if the bottom of the fraction is equal to 0. Remembering that's meant to be a z. So does 0, 0 satisfy this circle? Is it on this circle? And if we sub it in, we get 1's equal to quarter. It's not, so we don't have a problem. But had it have lied on that circle, then we would have had to excluded that point, because it wouldn't have satisfied the original formula that we're working with. Okay, let's try another one. This time they're telling me W is purely real. W is already the subject in this one, so I don't need to rearrange it. So purely real, purely real. Okay, as I say, I could do it algebraically by saying that the imaginary part is equal to 0. So if I do that, let's break it up into its real and imaginary parts. I'll realise the denominator, and I've got this wonderful expression on top. I don't need to expand the whole thing out, however. I don't want to waste time, Because remember, we're just interested in the imaginary part. The imaginary part is equal to 0. So if the imaginary part is equal to 0, that's all I'm concerned with. The bottom of the fraction doesn't matter, because when you have fraction equaling 0, it's always the numerator is equal to 0. And on the numerator, we've got two expressions there which are imaginary. We've got the minus x plus 1y, and we've got the x minus 1y. And so really now that's all I have to solve. So let's play around with it. We've got some xy's that cancel. We've got y equals 0. Or the x-axis, or the real axis, I suppose. Okay. Now, but notice, again, I have to go back to the original question. There's w. Z can't equal 1. Because if z was equal to 1, I'd end up with 0 on the bottom of the fraction. So I have to exclude that point. So that's if I did it algebraically. If I did it geometrically, and I'm thinking about it as a picture, then I'm saying, well, look, the argument is either going to be 0 or pi. So the argument of z plus 1 divided by z minus 1 is 0 or pi. But we've got a rule that allows us to break that up. So what this is saying is if I join z up to negative 1, and then I join z up to positive 1, the difference in the arguments will either be 0, so they'll be the same, or pi, difference of 180 degrees. So the question is, where on earth could we put that? So there's 1, there's minus 1. We're talking about rays, remember, because the argument is equal to a particular number. In this case, it's just argument of a linear function. I could have this situation, you'll notice. I've started at negative 1 and 1, the two red rays. They're going in opposite directions. And so their argument would differ by pi, or 180 degrees. Or, I'll just fill in the middle bit now, I could send them in the same direction. And if I send them in the same direction, then their argument difference would be 0. So what we'll end up with, we'll always end up with a straight line in this situation. So all we really need to do is join up the 2 points, and we know the line that joins those 2 points will become the locus in this case, if the difference between the two arguments are 0 or pi. Because if you put it anywhere other than on that straight line, imagine I put it like this. There's minus 1, there's 1, and I said z was not on that same line, then how on earth are we ever going to get a situation where these arguments are the same if z's not on the same line? And also, how could they differ by 180? Because we know the exterior angle of a triangle always adds up to be the other two, and the angle sum of a triangle is 180, so there's no way just those two could differ by 180. So they have to be collinear. Z and those 2 points are collinear. Now you'll notice I've circled minus 1 and 1 because I'm using rays, and we said whenever you use rays, you circle the starting point. Now, there's the subtle difference. In this first approach, I just excluded the point 1, 0. But in this one, I've excluded both points, 1 and negative 1. It all comes down to what is the original question. This is where I would go, okay, but I'm using this question to solve this problem. Actually, negative 1 does work. Because if I sub negative 1 into there, I get that odd number 0. Is 0 purely real? Well, yes, we put 0 in the real numbers, don't we? So negative 1 does actually work for the original question. So it does come up with the same answer when I consider that. Had they asked me, what's the locus of argument of z plus 1 and z minus 1, then I would exclude both points. Because when I sub minus 1 into this one, I'll get argument of 0. Well, you can't find the argument of 0. I mean, what direction is it going in? So it all depends on what the original question is. Here, in the second one, I changed the question to go and solve it, but it gave me a slightly different answer. So I have to check.
Do you think they could specify which
Nah, I'd find that unlikely. Find that. They might force your hand by having part I go and do this, so you've got some of this information already, and so you'd go, well, I might as well go that way, I've already done some of it. But I don't think they would specifically say, do it this way.
What information do they give? Like draw the two rays?
Yeah, maybe they might have just had a really simple part I. Draw argument of z plus 1 is this, or something like that. Yeah. Okay, let's have a look at this one. This is the one that I said will turn out to be the arc of a circle. Now, how do I know that? Well, let me show you how I know that. Okay, argument of z on z minus 4 is pi on 6. So again, I split it up and say, well, the difference in the arguments is pi on 6. I'll go straight to the diagram for this. Okay, so if I join z up to the origin, so z's somewhere on this ray, and I join z up to positive 4, at some point those two rays will intersect, and the difference in the arguments is pi on 6, so it's quite easy to show that this angle down here would be pi on 6 via a bit of geometry. So it'll match the angle. Now, what we're saying is it doesn't matter where z goes, the angle subtended from these 2 points is always pi on 6. Well, that goes back to our circle geometry. Remember we said angles subtended by an arc in a circle are always equal. And so therefore, this must map out. If I was to put every possible z, it must map out that circle because we've got angles in the same segment. Okay. Why is it below the axis? Well, let's have a look at what the question's saying. It's saying argument of z minus the argument of z minus 4 is pi on 6. So arg z has to be a bigger number. But if you look at our diagram, if I was to put it above, like say this one here, let's just change the numbers. That was 0, and that is 4. Let's call that alpha, and let's call that beta. So alpha, we're saying alpha minus beta is equal to pi on 6. In other words, alpha must be bigger than beta, but if you look at my diagram, if it's above the axis, there's no way alpha will be bigger than beta. Impossible, because beta is the exterior angle and it adds up to the sum of the other two. Can't happen. So that means it's below, and the reason it works when it's below is because now we're dealing with negative numbers. And so we're saying negative small number minus big number, it'll get you a positive number. Okay? So think about it above first of all, because that's probably the easier one to think about, the triangle above. Is this one bigger than this one? And if the answer is no, must be below. Must be below. So all right, we've sorted out it's below. I know it's going to be the arc of a circle. I define a circle with a centre and a radius. So that's what I now need to find. But I know perpendicular from the centre will bisect the chord. So 0, 4 becomes a chord of this circle we're going to draw. So I know that the perpendicular from the centre must go through 2. Let's actually draw it in. So somewhere down there, there is the centre of the circle. How do I know it's below and not above? Comes down to the size of the angle. It's pi on 6, so that will create a major arc. Remember we said if it was less than pi on 2, it'll create a major arc. Think about a major arc of a circle. Which side of the chord is the centre? It's on the same side as the arc, so it must also be below. So I know it's down below. Just got to find why. Bit more circle geometry now. I know the angle at the centre is twice the angle at the circumference. So this big angle here must be twice pi on 6, but if I just look at this little right angled triangle, then the angle there must also be pi on 6 because it would then chop it in half. So I can now, so that's going to be 30 degrees or pi on 6. The radius then will be the hypotenuse of this right angled triangle because it's going from the centre to the circumference. So let's have a look at that. Bit of trig. Y over 2 will be the tan of 60. So y is 2 root 3, except it's underneath, so it'll be negative 2 root 3. So there's my centre, negative 2 root 3. And a bit of Pythagoras, I can find the radius is 4. So I've got all the information I need now. What a great answer. Look at that. The locus is the major arc of the circle. X minus 2 all squared plus y minus 2 root 3 squared equals 16, formed by the chord that joins 0, 0 and 4, 0, but not including those points, because of course they were the beginnings of the rays. And if we go back, both must be excluded, because if you look at the original question, 4 is not going to work because I'll get 0 in the bottom of the fraction. 0 is not going to work because how do I find the argument of 0? I can't. So both points are excluded there. Wow. Oh, yeah, okay.
What does that arc look like in the diagram?
Where would... Okay, hang on.